This is Unit 3, Video 7. In this video, we'll continue talking about the electron domain and molecular geometries, except we will talk about them for the expanded octets. Remember, period 3 elements and on can have more than 8 electrons around the central atom, and we have to talk about the geometry that they produce. There are 2 more categories then. One with the 5 electron domains around it. This is called Trigonal Bipyramidal, and it's represented by this shape. Now this is called Trigonal Bipyramidal because there is a triangle base here. You can see it outlined right here. But there are 2 pyramids you can build from it. One that goes up and actually one that goes down. So it's like 2 pyramids that share a base, and that's what we call them trigonal bi, meaning 2, pyramidal. That's if you have 5 electron domains, a total of 10 electrons. If we have 6 electron domains for a total of 12 electrons, we get something called octahedral. Now the structure is here, and octahedral actually has, it's a shape of an octahedron. So it's a 3-dimensional, 8-sided figure. What you have, you actually have a 4-sided pyramid. Here is a 4-sided base, and you technically have a pyramid that has 4 sides. And you actually have them stuck together. But the shape is called octahedral. We have 8 equivalent sides, the octahedron. Alright, let's take a look at these in detail. So, now before we do that, let's actually say a word about, there are 2 positions in these expanded octets. There's what's called the axial position and what's called the equatorial position. And it'll be important to distinguish between them as we study these shapes. The axial is actually the one that goes up and down above the plane. The equatorial, from the word equator, is the one that sits essentially on the equator, on the plane. So these guys are actually in the same plane, whereas the one above, the one below, are out of the plane, and that's why we call it axial. Okay, now in octahedral geometry we have 6 equivalent, but both of these are the same. However, in trigonal bipyramidal they are not. What this means, here we've shown you the angles. Eventually we'll study the angles of these, but you'll see that the angle for the axial position up here is actually 90 degrees, whereas the angle for the equatorial positions is 120 degrees. 120 comes from the fact that you have 3 in a circle, and that's how you get 120. And 90, you have 4, essentially, and that's how you get 90. So we'll talk about these in a little more detail eventually, but realize there are 2 different positions in these. Okay, so let's talk about the one with 5, which is the trigonal bipyramidal. And the trigonal bipyramidal, having 5 electron domains, can give you 4 possible geometries. So this is kind of the biggest one. Now, if all of them have an atom at the end of it, in this case, then you simply call it trigonal bipyramidal, matching the electron domain geometry. If one of them is unbonded, notice here we have an unbonded pair, we will put the unbonded pair in an equatorial position. This is equatorial. Now this is important. We don't put him in the axial position, because equatorial position, so not axial. Because we say, well, what if we do put it in the axial position? As soon as you put him in the axial position, it'll actually switch, because the equatorial position is more expanded. And as we'll see, non-bonding pairs take up more space. So it's important to put it in the equatorial, not in the axial. Now this is called seesaw. And the reason we call it the seesaw, it actually forms a little seesaw. And this is kind of the base of the seesaw. These 2 arms, if you can imagine someone sitting here, someone sitting here, they kind of back and forth, they oscillate or swing, I guess, back and forth. And that's why we call it the seesaw. Next, if you have 2 of them, 2 are non-bonding pairs, then 2 go on the equatorial position. Notice again, this is equatorial. And you get this shape called the T shape. This actually is very logical. It looks like a T, just like a T, right here. And then finally, if you have all 3 are non-bonding pairs, this is as far as you go out, then all 3 go on the equatorial positions, and you have yourself linear. So you can actually produce a linear geometry from 5 electron domains, beginning with this trigonal bipyramidal. And actually, we'll see an example of this. Okay, and then finally, the last one called octahedral electron domains. This is if you have 6. And there are 3 possible geometries in this one. So actually less than in the one that has has 5. If all 6 of these atoms are bonding, this famously happens with SF6, sulfur hexafluoride, very fun gas that creates a very deep voice if you breathe it in. If you have all 6 of them, then you simply call the molecular geometry octahedral. Then, if one of them is an empty pair, then you call it square pyramidal. Now, in this case, it does not matter where you put the empty pair. So, it does not matter where you put it, where placed. In other words, it doesn't matter if you put it on an equatorial position or an axial position, you'll get the same shape because all of these are equivalent. In fact, they all have 90-degree angles between each one of these atoms. So it's called square pyramidal because it has a square base and it actually looks like a pyramid. And that's why it's called square pyramidal. And then if you have 2 electron domains, which is kind of the maximum that happens in these shapes, the 2 will go on opposite sides. Again, they go on opposite sides because they repel each other. So because this gives you maximum repulsion, and because this gives maximum repulsion, and this allows you to create a shape called square planar, and you simply have a square that all 4 of these atoms lie in a plane, so we call it square planar. Okay, we will show you some examples of both of these, and that's what we'll finish up with. So let's go ahead and use this VSEPR model to predict expanded octet geometry, and we'll actually do both as we've done before. Let's do electron domain, and then we'll do molecular. So draw it. In this case, let me draw it with you to make sure that you see this is an expanded octet. Remember, sulfur brings 6, each fluorine brings 7. You have a total of 28 plus 6, you have 34. Now, usually if you have a tetrahedral arrangement, you'll end up with 32 electrons. 32 because then each has 8. 8 times 4 gives you 32. So if you have 34, you know you have an expanded octet. But let's go ahead and draw it. In this case, you have 4 fluorines around the sulfur. And you've got yourself 34 electrons, so 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 22, 24, 26, 28, 30, 32. That completes the 32. If it were a regular molecule, it'd be following the octet rule. However, here we have 34, so we put 2 more on the central. You always put the extra one on the central. Now, what this does for us is it creates, let's check how many electron domains around the central atom. 1, 2, 3, 4, we have 5 electron domains. Our electron domain geometry with 5 is called Trigonal Bipyramidal. Okay, now 4 of these are bonding, 1 is non-bonding. So these 4 now have atoms, but this last one actually influences them. This one pushes the rest of them away. Now you have to probably go back to check what this looks like, but it will look like seesaw. So if you have yourself a central atom and you've got 1 above, 1 below, and then you have 3 lying in a plane like so, what will happen is, remember, one of them becomes an empty pair. So as this one becomes an empty pair, you can ignore it, but it's influencing the rest, and then you get the seesaw shape. Maybe the seesaw shape is a little bit easier seen if you ignore the other one. Let's try this. What if I ignore, put that one back. If I ignore this one, I think it's the seesaw shape is a little easier seen. So this right here then would be ignored, but it's an electron pair, and you can kind of see the seesaw that's looking kind of, that's standing vertically. If you were to align it like so, then probably a little easier to see the seesaw, hopefully. It looks like this. Maybe you see the seesaw a little better, maybe not. But the molecular geometry will be seesaw. Make sense? All right, let's try this last one. This is IF5. Let's go ahead and draw it as well. Iodine has 7. Fluorine is in the same group, so effectively you're multiplying 7 by 6. That gets you 42 total valence electrons to distribute. Iodine goes in the middle. Fluorine never goes in the middle. Fluorine will not allow himself to be of electrons. So we have 5 here, so when you draw 5 bonds, kind of do it like this, spread them out as far as you can from one another. We have a total of 42 electrons to distribute. So far we have 5 bonds of 10. Notice that iodine is already beginning with an expanded octet. So we have 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40. We have a total of 42, so 2 more go on the iodine. And that's how we get ourselves 6 around the center. So if you count them, we have 6 electron domains, 3, 4, 5, and 1 non-bonding pair. So our electron domain geometry in this case will be octahedral. The famous octahedral geometry. And then, as you see, 5 of them are bonding and 1 is non-bonding. So now we have to consider molecular geometry. This one here is then influencing them. In this case, if you do a similar structural drawing, you'll see that you began with 2 axial and 4 equatorial, kind of looks like this. And so what you do is one of them gets to be a non-bonding pair, and that non-bonding pair, doesn't matter where you put it, but we put it down here to kind of show you what's left. And what's left is a square pyramid, and that's what we call this molecular geometry, square pyramidal. You got square pyramidal for these. Okay, hopefully that makes sense. These are a little tougher to see. Again, we have models, molecular models, which we will use to visualize them a little better. And go ahead and try one on your own. Otherwise, this completes video 7 of Unit 3.